Good morning, everyone, and welcome to this new webinar by the International Energy Agency under our course on energy data and modeling for Zambia. So I'm very pleased to have you today again. I hope you had a good weekend. This will be our last week under our capacity reinforcement program and this first online course we are having together. And today we will discuss a very key topic to Africa and to other part of the world, which is the SDG 7.1 topic of energy access. And energy access includes two main streams. The first one is access to clean cooking, and that's why we'll discuss a lot solid biofuels. And the second one is access to electricity. So I hope this session will interest you. We will hear from Zakia on the first topic of solid biofuels and cooking, and then I will present on electricity access. So to remind you on where we are in our online course, this is we have one more session that will occur tomorrow. It will be the wrap up of the training with a quiz we'll do together. This is not an evaluation tool. It's more a way of interacting with many mentee questions. So we'll hope that this will interest you, and it will be a good opportunity to rediscuss all the topics we've seen over the course of the past 3 weeks. And we will also have a very quick closing ceremony, hopefully with the Minister of Energy of Zambia and the other key partners and representatives. So today, again, we will discuss these two topics of access to clean cooking and access to electricity, looking more into details at the case of solid biofuels. As we know, it's a very important fuel and energy in Africa, and there are many difficulties in collecting those data, in treating data related to solid biofuel. So we'll try to discuss that and also to see some modeling principles on how to deal with future evolution of access to clean cooking and solid biofuel consumption. We'll have a break with Q&A, and we'll also discuss the exercise that you have received, which is related to clean cooking. And in the second half of the session, we'll discuss access to electricity and off-grid electricity more specifically, giving an overview, discussing challenges on data collection, reporting, and treatment, and also discussing how to make projections for electricity access. So this is the plan for today, and I propose that we first start with a mentee question. So I will invite you to go to www.menti.com, and I will share my screen in a second. Okay, you shall be able to see the question and the code to answer this question, which is 48845252. So we'll keep this code all the day, and we will start with this first question related to biofuel. To you, how many kilograms of wood do you need to produce 1 kilogram of charcoal in a traditional earth kiln? Okay, so we have a bit of all the answers represented here. Even though most of you think it's 2 kilograms of wood are enough to produce 1 kilogram of charcoal. Of course, the answer will depend on the efficiency of the earth kiln, but based on data we have looked at, the answer is more 5 kg or even 10 kg of wood to make only 1 kg of charcoal with the most traditional and most basic earth kilns having only 10% conversion ratio, so 10 kg of wood to make 1 kg of charcoal. So we would say 5 or 10, depending on the efficiency. Thank you for your answers. I'd like to move to the next one. So as you know, there are several technologies that enable to cook under a clean way, in a modern way. You have a few of them which are listed here. According to you, what are the best solutions for achieving universal access to clean cooking? And you are proposed to rank all those solutions, knowing that you can of course answer with your specific national context, even though as we know the answer will be depending on the context of on the specific country, on its resources, and on the way people cook, of course. So thank you for your answers. I see that electric cooking is ranking very high, as well as biomass improved cook stoves, then LPG. A combination of all these options also sound sensible, as we it would depend, of course, on the context. Interesting to see that biodigesters is rated at last. Well, there is no, of course, good no correct answer. According to our analysis at a global level, we think that a combination will be needed, and that there can be an energy access ladder. Biomass improved cook stove can be a first step before moving to more advanced and more modern solutions such as LPG or electric cooking. But as we also know, there is some fuel stacking practices, so people may have more than one mean to cook. So it's usual that people have several solutions. Okay, one more question, which is out of curiosity. In your specific and personal case, what fuels do you use for cooking at home? Okay, I'm surprised I can't see the votes yet. Okay. Um, Thank you. So most of you are relying on electricity, but again, also see LPG and charcoal. And interestingly enough, so we have 13 participants, but we have 24 answers, meaning that several of you are using more than one fuel for cooking, which is one difficult aspect of understanding practices for clean cooking and understanding energy and fuel consumptions, as people are using a bouquet or a portfolio of different technologies. Okay, so thank you very much for your answers. We'll now move back to the presentation and hear first from Zakia on solid biofuels, how to treat them from a statistical perspective. We'll hear on Zakia about clean cooking in general, what's the status in the world in Sub-Saharan Africa, what are the recent trends, and when it comes to making projections, to doing modeling, what are the key parameters to take into account?
Let's get started with solid biofuels and access to clean cooking. We will look at the importance of solid biofuels in sub-Saharan Africa. Solid biofuels is an important and useful energy source in most African countries and is used primarily for cooking purposes and then for producing electricity. First, there is the cultural preference of some people who prefer to cook using firewood traditionally, but there is often an accessibility issue in rural areas for other sources of energy such as LPG, and so firewood is usually the most accessible fuel for cooking. In urban areas, even if modern fuels can be accessible, we might have the issue of affordability as these modern fuels are more expensive than wood. So even if alternatives exist, people still continue cooking using biofuels. Now let's see what are the impacts of using solid biofuels. The use of solid biofuels is not without consequence for the health of the population. Studies have shown that more than half of a million people die every year from pollution from biomass cooking. This is more death compared to diseases such as HIV, malaria, and tuberculosis. Other drawbacks of using biomass is that women also suffer from wood collection and spend several hours daily picking biomass. There are also safety consequences as they usually go alone in the forest. If the use of biofuels and wood is not done in a sustainable way, then there are negative impacts on the environment. If there is no balance, then the forest is reduced. It is also important to collect good biofuels data for policy making in order to guarantee that we ensure clean cooking access, proper regulations for charcoal production, etc. Therefore, tracking biofuels production and consumption is key for countries in sub-Saharan Africa. Now, let's put things quickly into perspectives and see how energy demand has evolved over the years. In 1919, wood accounted for around one-third of total energy demand. Over the years, we see how energy demand transitioned to oil, natural gas, etc. The share of wood decreased a lot at global level, decreasing from 30% in 1919 to only 4% in 2017. But in absolute value, biofuels rose by two-thirds from 400 mtoe in 1919 to 650 mtoe in 2000. Since 2000, as developing countries move away from the traditional use of biomass, the absolute consumption drops from 650 mtoe in 2000 to 620 in 2018 and 550 in 2040 based on the stated policy scenario. Now, if we look at final consumption, we see that in OECD countries, biofuels and waste is not significant, and in non-OECD region as well, it accounts for only 15% of consumption. However, if we look at Africa, the share increases to over 50%. And in Sub-Saharan Africa, it is even larger, accounting for three-quarters of total final consumption. We have seen that biofuels are the highest consumed fuels in Sub-Saharan Africa. In Sub-Saharan Africa, the biofuels consist mostly of primary solid biofuel such as wood and then charcoal. Now let us see more in details what we include under biofuels and waste. First, it includes primary solid biofuels such as wood, but also biogases, charcoals, bioliquids, as well as industrial and municipal waste. In OECD countries, we use mostly modern biofuels and also bioliquids such as biogasoline, biodiesel, and bioethanol. These are mostly used in transport, whereas for waste, they are usually used for electricity generation. Now, if we look at Africa, we see that it consists mostly of primary solid biofuels and charcoal that is considered as traditional use of biomass. And in Sub-Saharan Africa, it is, uh, it is even more primary solid biofuels. Now, let us see more closely at what are solid biofuels. Solid biofuels covers organic, non-fossil material of biological origin. We can make a distinction between primary and secondary biofuels. Primary production is the capture or extraction of fuels or energy from natural energy flows, the biosphere and natural reserves of fossil fuels within the national territory in a form suitable for use. Inert matter removed from the extracted fuels and quantities reinjected, flared, or vented are not included. The resulting products are referred to as primary product. Secondary production, on the other hand, is the manufacture of energy products through the process of transformation of other fuels and energy, whether primary or secondary, such as charcoal. Only the amount specifically used for energy purposes, that is a small part of the total, are included in the energy statistics. Let's see how solid biofuels consumption is evolving in different regions. First, we see that in 2018, Sub-Saharan Africa accounts for one-third of total solid biofuels demand, and if we look from 1990, we see a constant increase in demand that nearly doubled in the last 30 years. In the rest of the world, demand has remained quite stable. This shows that we are still increasing the use of biofuels and access to clean energy sources are slower than population growth that is increasing very fast by 3% annually. But where are solid biofuels consumed? In which sectors? In OECD countries, less than half is used in residential sector, mostly for heating purposes, and a big part is also used in industry for raising heat in industrial processes. However, in non-OECD, a big chunk is used in the residential sector. If we go to Africa, most of the solid biofuels is used in the residential sector and for cooking purposes. However, these numbers could be lower or higher because of data uncertainty. This graph shows household consumption for cooking purposes in rural and urban areas. And we can see clearly that there are some differences between rural and urban consumption patterns for fuels. In urban areas, we have a bit more fuel mix for cooking, where we have some use of LPG, kerosene, and electricity. However, in rural areas, it is still primarily fuel wood and charcoal. We often know how much kilo of wood that we collect, but how much energy does that wood contain? This is one of the barriers of biofuels data collection. The net calorific value, it's the useful energy, and the moisture content is also very important. Depending on how moist the wood is, the calorific value varies. Normally, when you cut or collect wood, it has a moisture content of around 55%. But if you dry the wood and reduce the moisture content to only 20%, then you see that the calorific content is more than twice than the wood with a moisture content of 55%. The efficiency of the combustion will be more, and it will be also more healthy. Now, if you transform the wood into pellets, then the calorific value is even higher. It is often the case in Africa that the wood is used fresh because of lack of space for storing and also the danger of being stolen. So in Africa, the average net calorific value of wood is around 7 megajoule per kilogram. And note that for comparison, that for LPG, it has a net calorific value of 50 megajoule per kilogram. So there's a big difference between the two. The production of charcoal is an output of a transformation process where wood is considered as the input. Note that the calorific value of charcoal is much higher than firewood. Note also here some important facts about charcoal production. The efficiency of the charcoal kiln varies quite a lot from 10 to 40% depending on the technology used, and in Sub-Saharan Africa, this is often very low. To produce 1 kilo of charcoal, you need a lot of wood, and in energy units, the efficiency can be as low as 20%. But if you have good wood, why do you need to transform it into charcoal? Charcoal is a better energy product. To have the same energy as 1 kilo of charcoal, you need to burn 2 kilo of dry wood. However, if you use moist wood, then you will need even more. Often in Africa, firewood is consumed without drying because storing it might mean it will be stolen, and there's also not space. So its quality when burned is lower. Firewood net calorific values are very variable depending on the type of wood and the moisture content when it is burned. In average, we can assume that it is 14 megajoule per kilogram. Charcoal, on the other hand, is a higher quality energy product with a calorific value of around 30 megajoule per kilogram. So it is more practical to store and transport charcoal because with the same energy you need less volume and weight. However, the transformation of wood into charcoal has a lot of impact. To produce 1 kilogram of charcoal with traditional earth kiln, you need up to 10 kilo of wood. So you need a lot of wood and so a lot of trees. Therefore, it can lead to deforestation if it is not done in a sustainable way and will affect the environment and lead to deforestation. However, with an improved kiln, it can be better and the yield efficiency is around 30% and you can produce more charcoal. So it is very important to track how charcoal is produced in the country as it has an impact on the environment. Let us look even more at the end use energy service that is cooking. Here we will see the different type of fuel, so wood and charcoal, and the means for cooking that is traditional stove and improved cook stoves. With a traditional stove, you need around 5 kilo of wood to cook a meal. But if you use charcoal, you need only around 1.65 kilogram of charcoal. Then to produce this charcoal, you will actually be consuming 16 kilogram of wood if using an earth kiln. So in the end, when you do a complete analysis, you are actually consuming more wood. The life cycle analysis shows an efficiency of 5% only. If you use an improved kiln to produce the charcoal, you are actually using around 6.7 kilogram of wood to produce the charcoal, and the life cycle analysis shows an efficiency of 14%. In an improved cook stove, you need just 3 kilogram of wood to cook a meal, which is better. And if you use charcoal in an improved cook stove, you need even less, that is only 1.15 kilogram of charcoal. If that charcoal is produced in an earth kiln, you will need 11.5 kilogram of wood to produce the charcoal, and the life cycle analysis gives a real efficiency of 7%. In an improved kiln, you need only 4.6 kilogram of wood, and the life cycle analysis or value chain impact is better and gives you 19% efficiency. Therefore, even if charcoal cooking is more efficient than wood cooking, at the end use stage, the impact on wood resources and deforestation can be much higher. With the increasing urbanization, the demand of charcoal could drastically increase if sound policies are not in place. Why do we have this impact on climate? If you have a forest, this forest is absorbing CO2 emissions and storing the carbon in the wood. Now, if you cut the wood and burn it, we release again CO2 emissions. And if we do this in a sustainable way, we have net zero emissions. And if there is an equilibrium, there is no net emissions. However, if the amount of wood is not cut in a sustainable way, that is, we cut too many trees, then the amount of CO2 released from burning the wood will increase drastically. And at the same time, the forest too will diminish, leading to a disequilibrium, and we will end up with positive net emissions as the absorption of the forest is much less. So if there is no net equilibrium, we have net emissions, which is positive. Now, let us move to the second point on the barriers and best practices for collecting solid biofuels. For biofuels, if we focus on primary solid biofuels, we see that all the products are combustible energy commodities which can be traded and stocked. The consumption of these products will be either as a transform to secondary product or as blended to the other sources or used directly in an end-use application. But how do we get these data? We get them from sales data, for example, from wood and charcoal sold in markets and consumption data. But here we also lose a big chunk of data as we miss the black market sales and also some people pick wood directly in the forest and so do not buy it. What are the common barriers? As you have seen, we have this issue of commercial and non-commercial fuels. But we also have a need to have a correct sample, and it is important to work with the statistical office of your country to have a representative sample for both urban and rural areas and also by regions. We need to collect data by type of solid biofuel used, as regional wood resources are different with different calorific values and moisture content. There is also the cultural difference to take into account because different people cook in different ways, etc. There's also different types of appliances, different cooking stoves. We need to cover both commercial and non-commercial biofuels and include charcoal as well. For non-commercial, we need to track how much wood is picked, the reselling, also the unregulated charcoal production. There is also a need to understand how charcoal has been produced in order to estimate the fuel wood input. So what type of kiln has been used? So is it traditional kiln or improved ones? Now, let us see what tools we have at our disposal to establish a methodology or an action plan to track residential consumption and biofuels demand. For the observed data inputs, we can find information from administrative data, surveys, and measurement. Using those input with some assumptions of calorific values, consumption of stoves, and energy by device, we can derive some estimations using modeling in order to have complete data output for energy by source, by end use, and also calculate indicators. Let's see a bit more the tools and data needs. This is not perfect, but we try to give relevance to each one. For example, if we leave it blank, then it means that it is not the best practice. But if it is green, it means that for this data need, this is the preferred data source. Estimation and modeling. Here we have to be careful as consumption patterns change, and we can't just assume that people consume in the same manner as 20 years ago. So there is also access to clean cooking to take into account. Note that it is important to continue collecting resources data, that is forest data, as well as charcoal production by type of plants. It is essential to track how sustainable biofuels consumption is. Now let us go even deeper into an action plan for solid biofuels data. How will we start? In 2010, let us assume we have a survey for household consumption by type of fuel. And we also know that the number of households. And with this information, we can calculate the total of charcoal, fuel wood, and LPG. Then for the next 5 years, we don't run any surveys and we just use qualitative data from census. Then we can estimate the missing years, but beware that we cannot use the estimate for many years as they lose their value over time. So if we use the qualitative data and and add it with the number of household by type times the intensity, we can calculate for 2011 up to 2050. In 2016, there is another survey that is done. And here we will get observed data, and this will also permit us to revise previous data, estimated and old surveys data if we collect even more detailed data. Survey results help us calibrate qualitative data for estimations. It is true that surveys are costly, but it is even more costly not knowing what is happening. Now we are going to deal with the last part of solid biofuels, and we will look at clean cooking status and modeling. Solid biofuels in developing countries are mainly used for cooking, a topic covered under the Sustainable Development Goal 7. There is the first target, which is 7.1, that ensure universal access to affordable, reliable, and modern energy services. And we have the indicator 7.1.2, which is the proportion of population with primary reliance on clean fuels and technology. How do we define clean cooking facilities? We have several technologies for cooking, and we define as not clean cooking technologies when we use biomass, coal, and kerosene. Note that for biomass, only the traditional use of biomass is not clean, and if you use an improved stove, it is clean. With this, we can calculate access to clean cooking. There are some complications to understand that, but because when you use an improved cook stove, there are different types with different efficiencies, and they also release smoke in different ways. So there is different CO2 emitted. For example, a basic improved cook stove uses between 20 to 40% less fuel than a traditional cook stove. But if you use an intermediate cook stove, you can reduce up to 60%, and an advanced improved cook stove, you can reduce by 50 to 70% fuel consumption. Same for smoke release, it can vary considerably. Therefore, it is important to know which cook stove a household is using, as the impact is different. Some people use different cook stoves for different meals cooking in the same household. So the task is even more complicated to collect all this information. At the IEA, we have tried to analyze the trade-offs between the different cooking fuels and technologies and gave them a score based on different criteria. There is the stove cost, so the traditional biomass is most advantageous because you just need to put free wood. For fuel costs, here you have to pay for electricity or LPG, and this is a disadvantage because here we have a problem of affordability. Then we take into account reliability, health impact, because if you are not using clean cooking fuels such as coal, this is a disadvantage for health. There is also the gender inequality, as it is mostly women that collect wood for cooking, and there is also the environmental impact to take into account. Now, let us look at an analysis that the World Energy Outlook team did on the status of access to clean cooking and tracking progress of what has been done lately. Globally, the average number of people without access to clean cooking has been stable since 2000. But if you look at Sub-Saharan Africa, the share has been constantly increasing, and in 2018, it reached 35% of the world. This is because population has been increasing faster than tools to help people access clean cooking facilities. The IEA has been working on energy access issues on the continent for nearly 2 decades. Africa's population is among the fastest growing and youngest in the world. The situation for clean cooking is more concerning, as the number of people gaining access barely exceeds population growth. Population relying on traditional use of biomass, kerosene, or coal increases from around 900 million people in 2018 to nearly 1 billion people in 2030. This has grave health, social, and environmental consequences, and the resulting household air pollution from traditional uses of biomass continues to cause 500,000 premature deaths a year. Now, why do we need to make projections for cooking? Making projections on access to clean cooking and on cooking fuels enable us first to estimate the number of people with clean cooking and track the SDG 7.1 indicators. It also helps us to better understand the future energy demand based on the portfolio of cooking technologies. It also helps us anticipate the supply of cooking fuels and its related investment. And finally, it helps us to assess the impact related to cooking, the health, climate, and environmental impacts. This is an example of fuel wood consumption and its impact on forests based on two IEA scenarios. The stated policy scenario is the scenario that is based on countries' announced policies, and the Africa case, it's a new scenario that achieves the continent's inclusive and sustainable vision for accelerated economic and industrial development, accompanied by the achievement of full access to electricity and clean cooking. Fuel wood consumption up to 2040 in the stated policy scenario keeps increasing in all these countries, and the forest keeps depleting. If we don't do anything, the impact on the environment will be terrible. However, in the Africa case, consumption of fuel would decrease, and so does the impact on forests because of less wood being cut. This is linked to an accelerated move away from the use of solid biomass and to the wide application of energy efficiency policies. The shift in the energy mix away from biomass towards modern energy sources such as renewable and natural gas results in major efficiency gains and accelerated uptake of other fuels for cooking. For example, cooking with LPG uses around 5 times less energy for one meal than cooking the same meal with traditional use of biomass in inefficient stoves. Now, let us see some of the key principles for modeling clean cooking access and the general principles for modeling as seen in the modeling sessions before. We need first to analyze the drivers such as population and cooking practices. With the drivers and some econometric analysis, we get the energy services demand, which is the useful energy demand needed to cook a meal. To cook, you need a portfolio of cooking fuels and equipment. You have to do a technology fuel reallocation. You can do a cost-based approach as well. So how many households will be cooking with LPG, will be cooking with traditional use of biomass, etc. in the future? Based on the efficiencies of these technologies and the useful energy demand, you can then calculate your final energy demand. And you can also calculate the amount of energy needed to produce in the country. The challenge here is how to allocate the technologies to population. First, not all households have access to clean cooking technologies. Therefore, we need to look at service demand separately for those who do and do not have access. For those who have access, there is a wider choice of technology and fuel based on fuel availability, cost, cultural preferences, etc. For those who do not have access, the choice is restricted and limited to the cheapest and free options and whatever fuel is available locally. Other options not available or not affordable, therefore they choose the traditional use of biomass, kerosene, or coal. We also need to look at how the number of people with and without access may change and what can drive this change. So, with policies and market evolutions based on characteristics of each fuel equipment, and also how and when will they gain access and shift to cleaner fuels and equipments. With all this information, we can derive the number of people gaining access. Let us look at some of the results that the IEA got based on analysis done. Our analysis showed that in Sub-Saharan Africa, the number of people without access to clean cooking will not decline drastically by 2030 in the stated policy scenario, which is the objective of the Sustainable Development Goals. So this scenario does not provide the right tool to achieve full access by 2030 and fix the affordability issue and the change in cooking habits. However, in the sustainable development scenario, where we achieve full access by 2030, we see that Sub-Saharan Africa, which in 2010 had less than 20% access to clean cooking, will reach full access by 2030. But how is this done? In 2018, 87% of the population in sub-Saharan Africa still lack access to clean cooking, and the fuel mix still has a lot of not clean fuels. In the stated policy scenario, more people gain access to clean fuels and technologies for cooking by 2030, but 70% of the population still lack access. To bridge the gap and achieve full access to clean cooking for all in the Africa case, LPG is the most scalable solution for urban settlements, with improved biomass cook stoves doing most to provide access in rural areas. LPG is the best solution as more than half of urban households gain access by 2030 as the population density justifies investment in the necessary infrastructure. In rural areas home to the majority of those without access, improved cook stoves are by far the preferred solution, dramatically improving the efficiency of bioenergy use. Electrification, biogas, ethanol, and other solutions also play important roles with their uptake depending on local context. Policies will continue to remain essential to push these solutions. In Côte d'Ivoire, for example, the national plan seeks to promote LPG use and increase efficiency of charcoal production. Therefore, despite progress in several countries, current and planned efforts to provide access to clean cooking barely outpace population growth.
So we'll now be able to take some questions. So please feel free to raise your hand or to use the Q&A functionality if you have any question on what was just presented by Zakia. So we have Sydney. I see you raise your hand, so you shall be able to speak. Hi Sydney, can you hear me? Are you able to ask your question?
Hello?
Hello, yes, we can hear you.
You can hear me?
Yes, we can. You can ask your
Okay,
question.
thank you. My contribution regarding LPG is that there should be deliberate policies to market and promote LPG use. So far, LPG has come with a lot of mixed feelings for various households, especially on the aspect of safety. So you find that usually households don't feel so much safe to use LPG gas cooking systems because of the health hazards that may come up with it, as there could be leakages of gas and so forth. That has apparently caused gassing and also some terrible household fires, actually. So there should be some sensitization on the safety aspects, some assurance so that LPG can safely be used, and then also a deliberate policy of supplying the LPG cooking systems. For instance, LPG cooking systems could be supplied in massive quantities at commercial facilities where households keep paying for the cooking systems, probably monthly, like rented out. That would be a positive move. Thank you.
Thank you very much, Sydney, for your remark. That's excellent, and I really agree with all you mentioned regarding this mixed feeling at household level due to safety. Indeed, this is one key issue to tackle, and maybe it can be addressed by ensuring that the supply chain is well standardized and supplied. My understanding, but I'm not an expert in LPG, is that those issues with gas leakage and potentially fires happen when there is some illegal refilling on, or when there are some players who don't abide by all the standards which are required to handle LPG refilling and treatment of the bottles and the cylinders. So it's more of a supply standardization and ensuring that at this level there are some good practices. But I also understand that there has not been so much or so many of these incidents, but indeed, if you have one, it's really striking the minds, and it can act as a break. But it's also very context and country dependent. In countries like India, LPG has really been deployed at a very large scale. Likewise, in Morocco, in Indonesia, without those safety concerns. So I think it's of course ensuring that the value chain is well professional, standardized, and working safely, and then also reassuring household that this can be a safe technology. Maybe on your last point, which may be related to affordability and the way of collecting payments on LPG. That's often an issue because for an household to move to LPG, there is quite a significant upfront investment to be made, because you have to to invest or to purchase the burner itself and all the equipment. Plus, you have to usually pay a deposit for the cylinder, and then to pay for the gas that can be that can be in a large amount. So this can make a very important upfront cost. And this is why there are some innovative approaches and companies which are trying to distribute LPG under pay as you go or pay as you cook business models, relying on the mobile payment, so that you can unlock your LPG cylinder as you need, based on your cooking needs, and you pay day after day depending on your consumption. So this is something that can be a solution to ensure or to increase affordability, and to make it easier for household to sustain and to afford the use of LPG.
Yeah, thank you very much. And then the other point is on the human capital in terms of skilled personnel to do the installation of the gas systems for domestic use. For instance, I bought a gas stove a couple of months ago, but up to now, I've not yet had it up and running because I've not yet invested in the reticulation of the gas network at home. So that is another case which actually requires a skilled manpower to do the installation and so forth. You find that these gas stoves are being sold in the shops, but there's no contact whatsoever to the experts to do the installation. So this is one of the challenges that we have to sort out.
Okay, thank you very much for sharing. I was not aware of such a challenge. We have tried to make some analysis on how many jobs can be created if governments heavily invest in clean cooking policies, supporting, for example, the distribution of improved cook stoves or supporting the expansion of LPG. And we have some interesting results. I don't have them in mind, but I'd be happy to look further and to share with you. But indeed, if we want the level of service to be sufficient, if we want safe and reliable provision of energy for cooking, this may require some manpower and some service, and this can be then for states a good return on investment. With many co-benefits as expanding clean cooking, but also creating some jobs.
Yeah, thank you very much.
Thank you, Sydney, for your sharing and for your question. I see there are others. One from Nolvazi on the how the price limit LPG use in household and how can the pricing and distribution model can be addressed. So I think I partially answered with those innovative business models we are observing. I know there are some startups working on it in Kenya, in Tanzania. So again, it's really pay as you go with small installment as you cook rather than paying upfront the full cost. And it's not only a question of the upfront cost at the day one. I understand that when your cylinder is getting empty, you will also need to pay for a full cylinder, and if it's a 6 or 9 kg cylinder, that would entail quite an important price. So I understand that a common practice for household is when the LPG cylinder is becoming at a very low level, households start using a bit more charcoal or other fuels to postpone the date they will have to buy again a full cylinder of gas. So again, pay as you cook models can be a solution. There are also some distribution models that can be related to microfinance, again, to have more regular payment and installments, or to have saving schemes to make sure that we break this idea of high investment occurring at day zero for the upfront initial investment, and then at every refilling of the cylinder. So there is one question on the statistics estimation on cooking biomass. So when estimating the figures for biomass used for household cooking, it was stated that sales is primary source of data. In your estimation, how big is the error in your results given that most of the cooking biomass is not traded? So that's indeed a very strong limiting point. I would not be able to tell you to give you order of magnitudes. I know that the UN FAO are working on cross-checking the data we have been using and new data they might collect from new surveys. But indeed, it's something which is very much coming from the field and not easy to capture. And I think the way we all work, that any time there is a new fresh data coming from a survey, from a field data collection, we update our hypothesis to make sure that it reflects more the reality. But that's not satisfactory enough, and there is still a lot of improvements to be made in understanding better the how biomass is used, how biomass is traded from production or collection point to the point of use. So a good question from Tendai. I have noticed from the IEA energy balance that the consumption of solid biomass is always increasing as population increase, while other forms of energy, coal, electricity, and to some extent oil products, as the economy fluctuates. May you explain how the modeling can allow a decrease in consumption while the population increases? I'm not sure I see exactly what you're referring to, Tendai. That would be helpful if you could reference some any findings, or where did you see other forms of energy decreasing? To answer very generally, and maybe elaborating on the way we make those projections. So when we will do some modeling, we will start looking at what final service do people want in the future. So how much cooking will people want, based on population, based on practices. And we will do the same for example, electricity consumption for cooling in the residential sector. So then we will come to final energy demand that in most cases will increase as population increase. And we will then allocate different technologies to meet those needs for services. We will look at different fuels that can make this final energy. So it will be highly dependent on the sector, on the process, but and also not all the fuels. But we can also add some constraint on the fuels. In the case of coal, as we all know, it's a very emission intensive source of energy or of electricity. So if we need to look at the different sources to produce electricity in the future and to meet future electricity demand, we might take into consideration policies to reduce the use of coal in order to reduce the CO2 emissions. That was a very general answer. If you can specify more where you saw other forms of energy decreasing, that would be very helpful. Thank you. So an excellent question on the best way to collect data on consumption of biomass fuel. The question is, can we just do modeling instead of extensive survey? So I think there is no ideal way. As we know, survey, each way of collecting data have pros and cons, or advantages and limitations. Survey can be expensive, can take time, but it can be also a very good way of getting a good understanding of what's going on in the field in reality. Modeling can be also a good way to fill in the gaps. So a mixed approach depending on the resources, depending on the objective as well. But there is unfortunately no one straightforward way that can be the best one to understand very accurately consumption of biomass fuel. So maybe one last question, and then I move to the exercise. Are we able to model the impact of improved cook stoves in the new policy scenario, taking into consideration that most governments are promoting the improved cook stove? So yes, we are doing this exercise. Let me maybe come back to the slide related to that. So here you can see the today's situation in 2018 and then projections by 2030 under two scenarios: stated policies in Africa case. Improve cook stove is the blue part of the pie chart. So under stated policies, which are the announced policies that we observe, which are put in place by government, we see an increase in improved cook stoves because there are indeed many policies to promote the use of improved cook stoves. This has many benefits because it can be an easy way to get good appropriation by household, because you're not asking them to change the fuel. For example, if you have someone using wood stick just under a 3-stone fire and moving but sticking to the same wood stick to be used into an improved cook stove device, you don't change all the way people are dealing with the fuel. They are still under wood, so that can be easier. You can also work on all the supply chain training, craftsmen and workshops to make those improved cook stoves, or to improve the efficiency standard of existing stoves and GECO and whatever the name to use for cooking. So that's an important way, and this is something in our Africa case that we see is needed to reach full access with more promotional activities from the government to ensure that, especially in rural places, we have a stronger use of improved cook stoves. And concretely, yes, we can model the impact of those improved cook stoves because we are taking assumptions on what is the fuel consumption on average by an improved cook stove. So what are the related emissions? So depending on our assumption of how much market share or how many improved cook stoves we will have in the future, we can deduct what will be the impact on CO2 emissions, also on investment, on number of people using these devices as a primary source. So thank you very, very much for all those questions. I will very briefly show the Excel exercise, and then we'll move to the second half on electricity. So here we are in the Excel exercise that was shared with you, a quick one looking at clean cooking and how we can analyze current data on clean cooking or cooking practices, fuel use, and how is it possible to make projections and to develop different scenario of evolution of those practices. So you were given historical data based on household survey, but also based on technical reports. So we are able to estimate how many people in the country are primarily relying on traditional wood stove, on improved wood stove, on LPG, on electricity. And the first question that you were asked is, calculate the share of the population which has access to clean cooking. This is an indicator that you might have to report under the SDG7 .1.2 indicator of the UN, and based on our definition, access to clean cooking requires to have some modern fuel or modern use of fuels, and that would mean here that electricity, LPG, and improved biomass cook stoves are under the category of clean cooking, whereas traditional wood stove are not. So basically, the share of people with clean cooking is all those using those improved solutions. That was question 0. Sorry, I can show you the answer. So the share is, again, all those not relying on traditional cook stoves. So it rises from 38 to 48% under our numbers. So the first question was to try to understand at a household level what is the annual energy need required for cooking services, and you were given some assumptions that can be refined and that can be adapted context by context, but you were given how much energy is needed to cook a meal on average, how many meals per day we expect, how many meals or days cooking at home versus maybe eating outside, number of people per household. And this, by multiplying all those factors, would give you the annual cooking energy need per household, and you can bring it down to a per capita level. And this number will be helpful to estimate at question 2 what will be the energy demand for cooking by fuel using the number of people relying on each fuel that were given at the top parts of the exercise, and some efficiency levels of each technology that are based on technical reports, on literature and research. So using those parameters, we'll be able to find how much energy demand comes from the need for cooking based on electricity in the country as a whole and how it evolved over time. We can see that this is something we calculated based on our survey and our calculation of energy need for one household or per capita for cooking per year. But we also had some information coming from the Ministry of Statistics, and then we can compare those data which are more bottom up and coming from our estimation with the data from the Ministry of Statistics. And that's what is asked at question 3. What's the difference between estimation and reporting data? We can see that for LPG and electricity, the difference is very limited. It's less than 5% delta, but for fuel wood, it's a 50% difference between those two data sets, which can be explained because, as we said, estimating fuel wood consumption is very difficult, and we might have been using old demand surveys which are not up to date because of the difficulties to track non-commercial activities, difficulties to track non-household, non-residential use of biomass. So what could be done is to, again, look at all those data and try to refine taking the latest available and to improve our data sets. Last question was about making projections and looking at 2 scenarios. So if we come back to our share of population using the different sources of cooking, projections under our under the stated policies were given. So we would expect, based on population growth, to have 15 million people cooking on traditional wood stove, 15 million improved wood stove, 10 on LPG, 11 on electricity. The new share of people having access is still the number of people using improved biomass, LPG, and electricity divided by the total. And the question is, can we make a scenario of universal access, and what would that take? So you were given some assumptions, looking at a specific policy from the government to support improved cook stove and aiming at distributing 5 million improved cook stoves in the country. So these 5 millions need to be multiplied by the average number of people per household to come to a capita number. Then we were also given some assumptions on the total possible supply of LPG, which is acting as a limitation because we don't project to be able to import or to distribute more LPG than 4 I think it was 4 terawatt hour per year. And last, we can deduct what electricity would be. It would be the remainder because we need to put traditional use of biomass at 0 because this is not clean cooking. So this is a very quick estimation that was done, a quick exercise just to show the possibility to work on those projections under clean cooking. So I don't see more questions on cooking. If you have more, please feel free to ask, and we'll answer in the second at the end of this webinar. But now I like to move to the second part, which is related to access to electricity. But before we'll start again with a few polling questions. So I invite you to go back to Menti for some questions on access to electricity. So we are still using the same code. If you joined us lately, the code is 48845252. And the first question is, according to you, what is the electrification rate in Sub-Saharan Africa? Okay, so you are all agreeing that it's 45%. I give you a few more minutes. And that's indeed the right answer. We have 45% of Sub-Saharan African population that has access to electricity. We'll discuss dynamics in a second. So another question. Let's look at regional breakdown. And according to you, what is the region that concentrates most people with no access to electricity today? I think you are asked to rate them. From the region that concentrates most people deprived of electricity access to the region with less. Okay, that's very interesting because so you are all from Southern Africa, and you are rating Southern Africa as the first region. Actually, it's not the case. We'll see in the coming slides what is the latest order and ranking. Okay, I don't disclose now the answer, but very interesting to see your vote. One more question, which relates to health centers. According to you, what percentage of health centers in Sub-Saharan Africa do not have access to reliable electricity. Okay, so we have quite a balanced vote. We'll see again some numbers we have based on surveys conducted recently. One last question relating to the best solutions to achieve universal access. So we're proposing grid extension, grid densification, mini grids or solar home systems, and you have 100 points to distribute to those different options according to their importance. So which option would you prioritize in a scenario where we want to achieve universal access to electricity in the continent by 2030? Okay, very interesting. Thank you for your answer. So grid extension is rating very high, and grid densification is at the bottom. So that's an interesting point. That would mean that where the grid is, there is no such need to densify it and to give further access to people which would be close to the grid but not connected. But on the contrary, grid extension would mean that there is a need for bringing the grid and the lines further to places which are not electrified at all. I can also see that solar home system and mini grids together would entail for 2/3 of the need to of the solution to provide universal access. So this is pretty aligned with some calculation we have done at a global level, but we'll discuss more in a second. So thank you again for your answers. I'm coming back to the presentation. And now, so in the coming 30 minutes, we will discuss access to electricity, more specifically the off-grid sector. And let's start with an overview of electricity access. So as you all know, the world is electrifying very fast, and you can see here evolution since the year 1990 with an index 100 in 1990 on how electricity demand has increased. You can see that it has almost tripled in Sub-Saharan Africa, and it has not so much increased in OECD countries. And this comes from bigger population, higher GDP, higher rate of access, so more population connected to electricity, but also because when we look at the per capita basis, there is more consumption because a household will have more appliances, more needs for electrical services like lighting, powering appliances, cooling, etc. Still, as we all know, access is not universal, and we have I'm sorry, those numbers date back to 2018. We have fresher numbers, but we have a bit less than 1 billion people still without electricity today, with many very dramatic consequences. And why does electricity access matter? As you know, this is the Sustainable Development Goal 7 and the 7.1 indicator to ensure that by the end of the decade, we are able to provide electricity access to all. And we often say that to us, energy access is the golden thread that really weaves together human development, economic growth, and sustainability, because it's related to many other SDG indicators. Just to take a few examples, SDG number 1 of poverty, for example, if a household can move from expensive stopgaps solutions such as kerosene lamps, which require regular spending of expensive fuels, and can move to sustainable products like a solar lantern, which has a limited upfront cost and then can operate at no cost. This can bring savings and help household move away from poverty. Energy also can power new economic opportunities, as we are all aware, and foster economic development. Looking at climate, of course, we can reduce greenhouse gases emissions and particulate matter if we displace polluting solutions such as diesel generators, such as kerosene lamps, and replace them by clean power from solar, for example. When we look at SDG 6 and 2 related to clean water, sanitation, and hunger, there is also a very strong water, food, energy nexus, where energy can bring improvements for agricultural productivity, for water management. SDG number 3 related to health, as presented by Zakia regarding clean cooking. We know that traditional use of biomass, such as kerosene for lighting, are important sources of indoor air pollution, and this causes more death than malaria, for example. So clean power can bring better health, but power is also required for health services and health centers to better operate. And one last example, which is also very obvious, is on the SDG number 4, where energy can foster better conditions for studying at home if you have a better source of lighting, but also at schools and in educational services. So to enter a bit more into details of incomes and energy, this is a famous representation of GDP per capita based on this is a function of the percentage of population having access as a function of GDP per capita. So we know very well this logarithmic curve, where you can see that if you increase a bit the GDP per capita, so the income, that would translate it into an important improvement of electricity access rates in the population, and vice versa. If you provide more electricity, that would boost wealth in the country. Looking at health and education, according to an analysis and to a research we have looked at, 60% of health institutions in the continent are working without reliable power. You can see that there are some high discrepancies across countries. Sorry, this survey is not on Africa only; it's global on emerging countries. And you would see that in a country like Niger, or Ethiopia, it's a higher share than for example in Myanmar, and that in some countries the use of off-grid solutions for health centers is already very prevalent, like in Cambodia or in Niger. due maybe to the grid infrastructure in those countries. If we look at education and electrification of schools, also under an UNICEF survey, we see that more than half of the schools of lower and upper secondary schools are not electrified. And here again, we can see that Kenya is ranking quite high with 80% of schools electrified. But in the case of Niger, it's only 10. And again, you have some countries who are making some use of off-grid technologies like Myanmar in Asia to electrify those schools. Okay, now let's look at our numbers on population without electricity access per region and relating to the question you answered in Menti. So this is the African numbers of population without electricity. And you can see that since, well, from the beginning of the century to the year 2010, it was rising to a bit less than 600 million, and it has remained stable more or less from then. But if we look at the global dynamic, what's impressive is that India, that in the year 2000 was concentrating as many people without access to electricity as Africa, has really managed to decline this number, and now India has reached universal access, and the rest of the world also has seen a decline in number without access. So this means that that the electricity access challenge is increasingly a Sub-Saharan African challenge. And you can see the breakdown per region, where Southern Africa is not the #1 region. It will be after West and East Africa. But the population without access to electricity in Southern Africa has remained stable over the last 2 decades. An interesting analysis we have conducted on the right is that we are often asked if it's feasible to provide universal access to electricity for Africa, because it means developing or providing electricity to 600 million people by the end of the decade. So this is very ambitious, but let's look at what happened in other regions. China, for example, managed to go from 600 million to 0 million people without electricity over the course of 35 years, between 1965 and the year 2000. India managed to develop the same trajectory, so bringing electricity to 600 million people in a bit more than 15 years. So considering improvements in technologies, especially with solar PV really becoming cheaper and cheaper everywhere, with storage also improving, and with much more knowledge and improvements than what China and India had at their disposal, there is no reason that we cannot achieve universal access in Africa by the end of the decade. Looking again at the region, the evolution we just discussed is that in the year 2000, India was the #1 region in terms of people without electricity, and it has really declined, having reached universal access last year. On the contrary, West Africa has become the #1 region with people without access. You might think of the fact that in West Africa, you would have Nigeria, which is a heavyweight, accounting for a bit less than half of the regional population without access, or 80 million people. Then in Central Africa, you would have, of course, DRC, which also accounts for 80% of the regional population without electricity. And looking a bit more at the rest of Asia, that concentrated many people without access at the beginning of the century, you had Bangladesh and Indonesia with 100 million people each without access in year 2000, and that come down to 20 and 5 million people respectively recently. In the rest of Asia, you still have countries with large population deprived, like Pakistan or Myanmar, but the trend is really to be reaching universal access by the end of the decade. And one more figure on recent progress managed achieved in East Africa, where you can see between the year 2018 and 2013 how much the electricity access rate increased. So in the case of Kenya, we have seen an increase by 50% of the electricity access rate, which meant 25 million people gaining access. A similar number has been reached in Ethiopia, while in Rwanda, we also have observed a very strong increase in the rate with a 30% percentage point rise in electrification rate. Another way of looking at this is the electrification rates and the share of population with access. And as we said, today in Africa, there is almost 45% electrification rate. Looking a bit more at regional dynamics, West Africa is the region with the highest electrification rate, above 50%. Southern Africa is just number 2 at also a bit more than 45%, which is consistent with the regional Sub-Saharan Africa average. And we have much more numbers because we are trying to track country by country what the number of people without electricity is and the rates are. So you would see on this map for Southern Africa that it's clear blue, meaning that the rate of population electrified is relatively high compared to countries like DRC, but you still have some countries accounting for many people without electricity, like Angola, Mozambique, or Madagascar. Maybe a more recent finding that we already presented to you is that looking again at the number of population without access, since the year 2013, we were observing some progress. So there were each year less and less people without access. And considering that population was growing, that was meaning that efforts to deploy electricity were outpacing demographic and population growth. So that was an excellent news. But with the pandemic in the year 2019, with the year 2020, we've seen progress being reversed because of the consequences of the pandemic. And we've seen the number of people without access rising again in 2020 to a bit less than 600 million. And actually, 5 countries account for half of those without access in Africa, including Tanzania and DRC. And we also think that due to the consequences of the pandemic and the aftermath of economic difficulties, many people that were connected to electricity are at risk of not being able to afford clean energy services and might come back to more traditional or more basic sources of lightings, for example. Okay, now we've looked a bit at the finding. Let's come back to maybe some definition because we've not started by defining electricity access, and this is indeed a challenge because there is no single internationally adopted solution definition. If we look at the solutions and the uses related to electricity access, you can see on this figure that there are many different technologies. We can think of pico solar or solar lanterns with a small standalone solar panel, an integrated lamp plus battery that might be able to do also radio and recharge a mobile phone. Then you have really solar home systems, which are bigger systems able to provide lighting and appliances like TV and fans to a household. And this is still standalone systems. Then you move up to mini grids, which are small infrastructure that can rely on different sources of energy, solar, but also wind, hydro. There can be also some thermal backup, some storage, etc. And last, there is what we all know very well, which is the grid. And those different technologies are more or less adequate to provide different type of services. When we look at the household and community uses, we can see that the more service we want, the more we need power under a high level, and we would need mini grid and grid. For example, cooling is not something that Pico Solar or standalone solar home system are able to provide, even though things are changing very quickly and we see more and more efficient devices that are powered under standalone solar home systems. When it comes to productive use for agriculture, for example, again, we see some interesting off-grid appliances like solar pumps, but traditionally such electricity-intensive services have been provided by grids or mini grids. And here, the IEA definition to what is electricity access is an electricity access that entails a household an initial access to sufficient electricity services to have a basic bundle of services like lighting, phone charging, radio, potentially fan and television, and the ability to grow over time. So concretely, in our numbers of people with access to electricity, we include those population who have solar home systems, who are connected to mini grid, or who are connected to grids. And once this is done, we can do much more analysis, because we were just here looking at what the technology and the solution at the household level. But as we quickly mentioned, it's interesting to look what is the source of electricity generation behind it. And we have conducted some analysis to see that, for example, you can have some different sources of power generation in central plants for the grid. And you can see here the brown part is coal, which has been an important source of generating electricity in many developing countries. But you can also see solar PV and decentralized renewables. If we zoom and look at the case of India, as we mentioned, India has experienced the fastest electrification process in history, providing access to electricity to 600 million people in less than 2 decades. But if we analyze what has been the fuel providing all those electrons, it has mostly been coal, because people were mostly connected to the grid with coal-fired power generation. Okay, let's quickly discuss different challenges for each solution. When we look at the grid, so as we know, this has been the traditional way of giving electricity access to population. It enables to provide a high level of services with very important voltage and level of electricity service. But there are some challenges related to reliability, related to losses. And I'm just showing here two analyses here on the share of population relying on backup generators because the grid is not reliable enough, and because there are many hours of electricity supply which are lost due to outages. So you can see that Nigeria is ranking very high, and that in the country 40%, there is a 40% annual outages in the country, while the average for Sub-Saharan Africa will be at 5 or 6%. And then many countries also are relying on electricity generation from backup diesel systems to prevent from grid outages. If we look at losses in the continent, based on our analysis, the average in Africa is at 16%. So these are the network losses coming from the grid, and it's much higher than the average in developing countries. And you can see some countries like Ethiopia, but you could also think of countries in the Sahel region like Mali, where the share of losses is above 25%, which means that a lot of the energy which is consumed for power generation is lost before reaching the consumption. Then another challenge for the grid is that you have some unconnected population today which are not easy to reach. There are some people living under the grid, so in a region where the grid is present, but those populations are not connected, maybe due to affordability or due to other technical challenges. And you also have, of course, low density rural population where it's complex or not economical to extend the grid. And this is where mini grids and standalone system can make a difference. Now coming to mini grids, there is a very strong potential for expanding mini grids in many regions of the continent, but there are also some challenges. I just mentioned a few of them. In terms of finance and economics, capex or investment expenditure are very high for mini grids, and opex are also important and often underestimated. For example, the operation and maintenance cost. And on the contrary, revenues are uncertain, with often some risk of low consumption or low ability to pay from consumers. Basically, to have a mini grid that can run sustainability, you often need some high level of investment, potentially subsidized, and you also need to have some very bankable or generous anchor clients, like a telecom power tower, or a big infrastructure like a hospital, or a big industry like a mining site. And once you have this reliable customer, you might be able to extend the lines and power the community. But this kind of scheme are often necessary to make sure that the mini grid can be economically sustainable. Then there is a question on scalability, because each mini-grid site is specific. There is no standard project. You need to study what the potential supply is based on local resources. Is there a small river? Is there a wind potential? What is the solar irradiance, etc.? On the demand side, you also need to estimate what demand will be to make sure that you size correctly your project. And for each site, you might have some administrative process that can be long, or some challenges to really develop this small infrastructure. And then regarding planning, there is always those questions on what happens when the grid arrives. There are many ways of addressing that, but that's still somehow a question to be addressed. And last, we have the standalone solar systems. So as we said, this is some technology which has improved very fast, with now some very high efficient systems where you can power a TV, a fan, several lighting bulbs, having a battery and a solar panel on your roof for an affordable way, and under a pay-as-you-go business model, where you don't need to invest upfront, but you can pay day after day using mobile banking and locking and unlocking technologies. But those products such as solar lanterns also come with some challenges. It's the main bottleneck is about distribution, because you are no more under an infrastructure energy approach. You are more like FMCG distribution, or like the telecom industry distribution, where you need to penetrate very deep in rural areas and to distribute your projects and to maintain them and to be very close to your customers. Then increasingly you need to leverage digital technologies and to ensure that your customers have ability to use mobile banking, for example, to make the payments and to manage the relation remotely. One key issue is about recycling, because if you deploy many solar lanterns, for example, there are questions on sustainability of those products, depending on their lifetime and on the approach you can implement to get back those products and recycle. And last, those standalone systems and solar lanterns have been mostly deployed by private sector under market-based approach, but market-based is can be relevant, but cannot serve everyone. So if we take the case of refugee camps, or also looking at other share of the population which are not bankable, there is some need for public support or subsidies to provide electricity solutions to those populations. So just sharing with you one country example, which is a case of Togo, where they come up with a very interesting integrated plan to combine all those solutions. So here you can see the map of Togo, which, as you may see, is a country in West Africa, which has a very interesting geographical shape, because it's I think it's maximum 50 or 60 kilometers from east to west, and it's around 800 kilometers north to south. And there is today a high voltage line going from north to south. So you could think, if I want to reach universal access, it should not be too complex to just extend the grid, because based on this high voltage line crossing all the country, I just need to draw some lines horizontally or west and east, and this will not be more than 20 kilometers from the existing lines. But even with this geographical shape, it's not economical to extend the grid everywhere, and instead mini grids and solar home system are required. And this is what the CISO integrated strategy of the government has developed with grid. Sorry, the slide is in French, but you would understand that a grid is on the hands of the utility and the government, while mini grid and solar home system will be developed by private sector companies with partnerships with the government, and they will operate under license and receive subsidies and support, and share back with the government some data on the number of people which are gaining access. Sorry, so I go very quickly to one or two more slides, and then happy to take some questions related to data on tracking electricity access. So basically, this is an area where there is room for a lot of improvement, and we will be very happy to work with all of you, with the government of Zambia and with other countries, to improve our understanding of electricity access data, because today there are basically two sources of data. So number one is surveys, which are, for example, relying on DHS or demographic surveys, where you would have someone going to 5,000 households in the country, asking a series of hundreds of questions, including, do you have access to electricity, or what do you use for lighting? And based on that, you would extrapolate and get a percentage of the population with access. And the second one, which is what the IEA is relying on, is government reported data coming more from the supply side. For example, the utility able to share numbers on the connections to the grid. And sometimes we see government which also consolidate numbers coming from mini grid operators or solar home system distributors. So there are also new ways and new topics we're trying to work on, trying to go beyond this binary information of connected, not connected, but understanding availability, reliability, quality of the connection, and also getting all information not only on household but on health centers, public buildings, etc. There is, of course, the World Bank multi-tier framework, which aims, based on surveys, to capture better the level of service and the quality of service provided. There are some, I have this slide I made based on the Zambian example of the Edison platform, but I'd be very interested to learn more from you on how is this going. I understand that this platform is able to track live the number of connections under the Beyond the Grid Zambia program, looking at number of people gaining access by mini grids, but also solar home system distributors. So this is also something that interests us a lot. We can see also some new sources of data based on geospatial satellite data, tracking household lighting points and rooftops, solar panels. And I stop here so that we can have some questions. But again, very interested to learn more on the experience of Zambia in this off-grid space. Okay, so thank you. And if you have some question, I'm happy to stay connected to address them. Okay. As you are writing question, you might have seen that I did not cover the last part that was modeling. How do we make modeling on future electricity access? To comment very briefly, this is about understanding how population will evolve and how population with and without access will evolve, and then what the energy demand from this population will be. And we proceed all that in our models to anticipate and consolidate with other sources of electricity demand. And then, as always in the power sector, once you know the need for electricity, you can look at how to supply this electricity to meet this demand based on the different sources and your different technologies. So here again, we can have solar home system in maybe the most rural places, mini grids, and also grid extension densification based on where it makes most sense to develop them. And based on that, I can briefly show based on some geospatial analysis we have conducted looking at where people are, we have been able to propose and to shape some best least cost pathway to reach universal, depending on those different technologies. And from there, we can derive, for example, the investment required, what would be the impact in in terms of people gaining access, in terms of CO2 emissions, etc. So we've been running a bit late, so I don't want to keep you too long. If there is no question, we can stop here. I just want to give you 1 more minute in case questions are coming. Okay, so I'd like to thank you for your participation, your time, and your attention today. I hope you enjoyed the session. Tomorrow it will be another interesting one to wrap up all that we discussed. So it will start at 9, and that will be the last one. We'll share also some information, some important information on what's coming next for our training. So thank you very much to all of you, and have a very good day.